Alright, so in this one what we're going to do is we're going to make a bunch of claims and connect together a bunch of facts that will help us describe why flow augmentation is actually effective. So let's start with something that's really important, and that is we need to start with the definition of, this is something I alluded to in the last video about flow across a cut. It needs to be equal to the actual flow in the flow network. So we should have a definition for the flow in a flow network. And this is really just a place to start. Once we make a nice little theorem, there's going to be tons of ways to calculate the flow in a flow network, but this is a good place to start. So the flow in a flow network is the amount of flow leaving the source. Okay, so whatever's coming out of the source will be the flow in a flow network. All right, theorem. So given any cut ST, the flow across ST is equal to the flow in the network. Okay. More specifically, we would need to show that the flow across any cut is equal to the flow coming out of the source. All right. So I'm not going to actually do a proper proof here, but let me give you a sketch of the idea. Okay, so what you would do is you would build S inductively. I have done this in class before, but it takes about a half hour to do properly. Build S inductively. And what you do is, of course, you have a base case, which is just the source, right? Which is not S yet, but you're going to keep adding nodes until you build all the way to S. You just need to build in a connected manner. So you find a node, and actually you don't have to do this connected manner, but usually you start with those. Those are the ones that are interesting. So you take your base case, which is the source, and you add a node. First of all, this is true by assumption, right? The flow coming out of a source is going to be exactly the flow across this preliminary cut. And then what you do is you keep building. So you add vertices, add one node at a time. And then you use conservation. Okay. So because every flow is conservative at the nodes, you can't actually create any more flow or reduce any. And so that flow number remains the same every time you add a node. All right. And so you can build all ST cuts this way. Let's see. Okay. So let's give this a name. F. Okay. So just F by itself. Okay, so the flow across any cut ST is equal to F, and this is true for all ST, right? So this is independent. So what this also says is it doesn't matter how you cut the graph, the flow that you calculate is going to be the same number no matter how you cut it. Okay. Now this is not true for capacities, all right? Capacities have different numbers based on S and T, has nothing to do with flows whatsoever, at least in terms of calculation. So capacities do vary based on S and T. However, one thing is critically important, and that is, one thing that's always true is the flows are always less than or equal to the capacities across any cut. Okay, why is that the case? Well, I don't think I need to write it here, but go back to the last video about how to calculate these two numbers. Remember, flows are confined by capacities already, but in addition, this could even have subtraction on top of it. But with the subtraction aside, this thing is still capped by these capacity numbers. Okay, so this is always true. Okay. All right, now, here's something interesting to note. So if the flow across a cut computes to be equal to the capacity across a cut, it turns out then the flow is maximal and the cut is minimal. In the sense that the flow is as big as possible and the cut has the smallest capacity possible. Let me explain why. Okay, this isn't really like a cut or a flow issue. This is a question about having two groups of numbers. Okay, so you have a flow number for every cut and a capacity number for every cut. So let's call these number groups A and B. Okay, if I take any number in A and compare it to any number in B, any number in B, I actually am able to compare them in this context. All right, so one thing that's important about these is, right, this number is the same for all of them. And so these numbers are always bigger than any of the ones here, right? So A is less than or equal to B, and this is true for all of them. Right, so if I take the biggest A number, the biggest one I can find, usually you don't write it with the subscripting like that. We don't need that extra indexing, sorry. This also saves me a line. Take that biggest one. Its biggest one is going to be bigger. This biggest one is going to still be confined to be less than any of the B's. So it's less than or equal to the smallest. So if I achieve equality, then I have simultaneously found the biggest A and the smallest B possible. This is just a property of having two groups of numbers when you know that any of these numbers, so any flow, is capped by all of these capacities and vice versa. Okay. So, so if you can find a flow that matches a cut capacity, then you've simultaneously known you found a maximal flow and a minimal capacity. All right, so some things that are going back to sort of thinking about this in terms of flow networks and capacities and cuts and all of these issues. These cut capacities are different numbers for different cuts. And the smallest is the bottleneck in the flow network. And so if you can fill that bottleneck, you've gotten kind of the maximal flow possible. So this is a bottleneck detector. Right. And one thing that is quite helpful about flow augmentation is flow augmentation will actually identify a bottleneck for you. Right? And that's quite useful. All right, so I don't think I have room on this one, so I'll have to do it on a separate one. But what we'll do is we'll do another flow augmentation. If I bring back one we've already done, we'll do a flow augmentation and we'll use these ideas to look at the cuts, check the flow, check the resulting cuts and see that they match, and see how that works. All right, so I'll see you on the next one.